Good day to you, wherever you are watching from in the world. My name is Stefan Moret. Welcome to the session as part of the Full Stack Actuarial Conference. So you think you can code? Um, it's a little bit of a tongue-in-cheek topic, but it's really about, I guess, my experience with the Dunning-Kruger effect, where initially you think you've got it all figured out, and you think you can code, and then you realize over time, and the more you learn, you realize how difficult coding really is, and being a good software engineer. The software engineering industry is really young. For example, the actuarial profession is much older, and it's a profession that has best practices established. But the software engineering industry is really figuring things out. It's still in that phase of figuring things out, and there's some really fast and recent learnings, and we as an actuarial profession can actually learn from this because coding and actuarial are becoming more intertwined. The technologies that coders use and the technologies that actuaries are used are becoming more and more similar, and the field of data science is influencing us. So that's the context. In this session, we'll be looking at software industry best practices and how they can be applied in actuarial work. So please take note of the following antitrust notice. And just thank you to our sponsors making this session possible. So just to introduce myself a bit more thoroughly, I'm based in Cape Town. I grew up here. I'm South African, and I'm working for a company called Dynamo Analytics, initially founded in the UK, in London, and who's now a global company. And the software I'm working on is a software called Cycle. So Cycle is an ecosystem where your models can live and where the actuary, the user, can build and maintain their models using low code, some code, some user interface based configurations, and the idea behind the software is to automate everything and reduce the amount of time spent on manual tasks at month end as much as possible. It integrates with a business system, and it's really a place where business process can be built, or actual model can be built as part of a business process, and that's the way we think about it. So just to give some business context, and I think this is a similar context that many of you are probably working in and trying to solve problems in, and so basically, actuarial processes, we see them evolve over time. They are built up not initially in its desired state, and often they are a little bit convoluted because of their history and using a mix of legacy processes, legacy softwares, and it sometimes it's really complex, and sometimes it's not complex enough. And sometimes we rely on manual processes a lot, maybe at month end, where you need to manually go to the data team and pull your data instead of treating your process like a data pipeline. And often the business and regulators require more and more transparency of your assumptions. It's not always You're not always able to see what overrides have been made, what assumptions have been set, and then you're really just turning over models and producing year-end results for an insurance company, or running a capital modeling process takes days, where in theory it should take you only a day or perhaps minutes. On top of this, the industry changes. The insurance industry faces various challenges, and actuarial teams need to adhere to increased complexity in accounting standards or modeling requirements, and There are various practical challenges. For example, it becomes more and more difficult to reuse code effectively. Very like poor model governance, and versioning is a challenge. It's difficult to collaborate on these models together, and to effectively distribute tasks. And then we're sitting with poor performing code, because perhaps we're not using the cloud effectively, because we are not software architects or system reliability engineers. And we need to start speaking that language in order to work effectively um, with IT teams. In preparation for this topic, we ran a survey. We specifically looked at actuarial teams maintaining code already, or teams that are comfortable with coding. We looked at a couple areas for ETL, extract, transform, load. The most popular technologies were SQL and SAS. For modeling, it was Python and still VBA. And then for process orchestration, also VBA and Python. And then for ad hoc analysis, interestingly, the most popular language was R. So 82% of respondents say that they already maintain in-house code for report generation, 53% for ETL, 71% for process orchestration. That's basically just stitching all your applications together and basically allowing them to flow from one process to the other automatically. And then 88% of respondents indicated that they maintain in-house code in one form or another for the model logic. And then this was a very interesting question. So basically, we asked, what is your technology strategy for various teams? So 6% of respondents indicated that they actually intentionally avoid maintaining code. 35% they have a strategy to intentionally maintain in-house code, and that's what they want to do. And 59% have a mixed strategy. So that is, they mix proprietary software and in-house code to find the optimal balance, and basically balance what their team can manage. And then only 65% indicate that coding, the in-house code maintained is through Git. And then 25% only indicated that they have automated testing in place. So this is a summary sort of the survey results, and it doesn't paint a great picture. So especially version control and, for example, automated testing. If this was a software engineering team, it would look like it's a pretty bad team. So to give perspective on why I say that, we'll look at the traditional workflow in software engineering, which originally just came from generic engineering projects. You start by defining the requirements for your app that you develop, or your project that you're going to run. You then design the implementation, design the solution. You then build the solution, and you test whether it works, and then you effectively run with it in a business as usual context, or start running it in production. So what does this mean? This means it's going to cost a lot to make changes later. So for example, if you are in the testing phase already and you realize one of the requirements are wrong, you need to potentially redesign a lot. And some of you might have seen this, where someone responds to you in your team and saying, I haven't designed this model to do that. It also means that key decisions have to be made at the start. And effectively, this is great for simple and unchanging projects. It's probably the most effective workflow. It's called the waterfall workflow. So according to the book titled The Phoenix Project, the authors list a number of challenges faced by software teams traditionally, and how the teams have evolved over time. But looking at the traditional challenges, defects are passed downstream to further work centers. So traditionally, there's a dev team, and they might pass down problems to the ops team, who then just need to deal with it. And the teams work in silos. So the communication channel isn't always clear, and that is described as one of the main problems in this field. There's also very interestingly a massive challenge to look with hindsight at a certain project and be able to distinguish between what work mattered and what work didn't have any impact. And then this is something we can relate to a lot. So there's scope creep, and then just to highlight the last one, debugging is obviously, like, a lot of you can probably relate, but debugging takes too much time. Fixing and finding faults, that's one of the key challenges in the industry. And just to introduce Conway's law, organizations who design systems are constrained to produce designs which are copies of the communication structures of these organizations. So what that means is, effectively, if you want to build a better process, sometimes you need to look at your organizational structures as well. So, and this typically speaks to the dev versus the ops team, for example. Sometimes you need to break the barriers between your teams, or sometimes you need to break down your silos, and relook at how you manage your teams. And this might be a data science team versus an actuarial team. This might be a business team versus a testing team. So sometimes you need to look at those structures in order to improve your process and improve the software that you produce. So introducing the modern workflow in software engineering. Start by assuming that you are wrong, and then proceed in small steps, as far as possible, small incremental steps. And try to optimize all your workflows among your teams, the way you code, the way you work, so that you optimize learning. So learning from your mistakes, learning from experience, and then to be able to adapt and change quickly. And then another key thing is to rely on customer feedback. So this is typically a software engineering team would gather customer insight and lean on customer insights in order to improve their application as fast as possible. And then this is the agile approach. This is agile workflow. Described very generically. You can read more on the Agile Manifesto, and there's different variations of it. So it's a widely discussed topic of like how you should do Agile. It's potentially a bit of a can of worms, but I try to just explain it in a very simple way. This is suitable for large projects. If you just think about it objectively. And if there's a high level of uncertainty, and often if we're working for an insurance company who need to maintain a very complex and a key business process, often like the nature of the uncertainty of that business process is quite high and volatile, and sometimes the business requirements change quickly. So there's an argument for our business processes being more suitable for this kind of approach. So in software engineering, useful paradigms to help you implement this approach is to do test-driven development, continuous delivery, fail fast mindset, or like iterating quickly on different variations and trying things out quickly, and then I want to talk about domain-driven design as well, and uh, potentially using functional programming instead of object-oriented programming for everything. So test-driven development, it's basically a technique just to build software, but guided by tests. You start by listing test cases. So these can be key requirements of the solution. And then you pick one test, one of these scenarios you pick, and you basically write a structure around code that doesn't exist yet. That is basically like a unit test that tests whether this thing, whether the application can do this. It will obviously fail when you've built that test because you haven't implemented the feature yet, and then you basically just build to make this test pass, and then you improve. So that's the refactor part. And then as we learn, we update the list of test cases. So this might sound a little bit foreign to you or strange, and I've described it very quickly. But let's apply this quickly in actuarial work. So say we are tasked with rebuilding a life insurance pricing engine. And we would then start by perhaps taking a few very simple cases of what the existing solution produces. So just maybe there's an Excel model, and we need to rewrite it in some other software or using some other software, maybe proprietary software, or maybe it's a Python model or something like that. So we'll take a very simple input and the expected output and create a test case for it. So we start by that. Maybe a couple scenarios. Maybe it's maybe one complex case and one very simple case, and then we write a test for it. We start by creating our code or our solution that's like a placeholder with like no logic in it. And we just start by coding up or building a system which automatically checks, can this new pricing engine with this given input produce this, does it produce this result, like our new expected result? And maybe like for this exercise, it might be that you just rely on the old pricing engine to use that as your expected result. So what you would then do is, since it already, like when you run the test, it'll fail automatically because we have no model. We just build a very simple model. So we start by just catering and focusing on the most simple test case. Make that pass, and then afterwards improve it. We then pick another test scenario. So this might be a slightly different, basically a different kind of policy, maybe different product details, and we then basically update our code to also make sure that it can handle this test case or this member scenario, and then we spend the time to refactor the code again and make sure it's improved while we do that. And there might be some learnings. So we might find that the original model, the original pricing engine had mistakes or oversimplified assumptions, which we don't have to rely on anymore. And then we basically update our list of test cases. So we update our rules around this and make sure and document the process thoroughly. So basically this is an example of how you would apply test-driven development in an actuarial context. And then also just a very interesting thing to note, you can actually apply test-driven development on performing model checks. And I think that's a really, that's a good place for us to explore and to learn from. So learn from software engineering principles and the way they do unit tests and apply them to what we've learned in actuarial studies for the way we do model checks. So just introducing domain-driven design. So domain refers to basically the problem environment or the solution space is another word for it. It's the real world scenario where a certain software engineering team's application is used. And then a key thing to understand in this is a bounded context. So this is basically putting a certain logical border between and to separate different areas of the domain. So we'll look at an example in a second, just so you can understand that better. But when you apply domain-driven design, you effectively want to start by not coding. You want to first don't jump to conclusions. Don't think you understand the problem space really well. And I think this is, for us as actuaries, it's really difficult because we are often domain experts. But it's all about building up a conceptual model first before starting to build the solution. So you can use various tools for this. There's, for example, a popular tool is Draw.io, open source software for that programmers often use. You can use apps like Miro or just physical sticky notes to build this model. And you want to basically have sessions with certain business experts in your solution space or in the problem, the people that experience this problem, to make sure that they're that you engage that stakeholder and get their input into what the solution should really look like. So you first settle on this domain model so everyone's on the same page as to what needs to happen and what needs to be built. And this helps so much in ironing out business requirements, ironing out and just figuring out exactly the mechanics of what this thing that you're building is supposed to be doing, and making sure that you, as the person that needs to build it, understand it really well. So assume you don't. So basically, assume you don't know. You need to go and ask. That's a really good strategy. And then effectively, another key thing of domain-driven design is that you need to speak ubiquitous language. That basically means that the language that you use is the same language that the business uses or that the users will use, and the same language that you will then use in your code. So a key thing to strive for is that your code needs to be so, like naming and naming conventions and things in the code needs to be in such a way that a user or someone that knows the domain really well can just look at a certain piece of code and be like, oh, this must relate to the finance part or the billing part of the application or something like that. It must be obvious, like so that's something to strive for. And then so obviously after building the domain, you then actually proceed to write your code and structure it in such a way that it matches the domain model structure. So a key benefit as well is this domain model can be documentation to onboard new members. Let's explain this a bit more detail and make it practical. So applied in actuarial work, let's say we have a business objective. We are tasked with a business objective. We need to automate year-end financial results for an insurance company. We start by creating mapping out different business events. So that's typically creating, like maybe building an event model. So this is event model is just a visual technique of visualizing and capturing all the different events that typically take place during a financial year-end process. And we do this by consulting various stakeholders. So For example, a bounded context might be the reserving process, and then another bounded context within our domain is the capital process. And we would then consult the reserving team, or the people typically doing reserving, and to understand what typically happens. Maybe they start with collecting data from the data department. And then after the results, another key event is they need to send the results to the capital team for their process to kick off. And speaking ubiquitous language, we would use the terms that various business stakeholders understand, and perhaps not rely too much on actuarial lingo. I think what I've seen is actuaries love their acronyms, and they love to come up with their own naming conventions. But to the rest of the business and to the wider field, this could be just a bunch of lingo or jargon, and just make it really hard to understand what's happening. We would then, after building this event model and making sure that we've covered all angles, only then we would then proceed to build the solution, and really let that model, let that design guide you in how you build this code, basically, or the solution. Now jumping to continuous delivery. So the aim of continuous delivery is to allow you to make changes to your system without disruption, without causing disruption. And the key idea here is that the system is always in a deployable or the model in actuarial in a runnable state. This is done through pipelines. So those of you familiar with this, in data science, you also get data pipelines. Data pipelines are slightly different to this concept. So CI/CD, so continuous integration and then continuous delivery, typically involves automated executions, code that is run in the cloud that compiles your code for you, for example, that runs tests for you, that might run integration tests, and then deploys this automatically to a staging environment where someone could go and perform some manual checks, and then finally deploy this to production with as little friction as possible. A key thing here to understand is that I, as a developer, if I make a code change and I push my code change in Git to the main branch, it always compiles. There's a check that literally prevents me from pushing changes that breaks the system or that causes the code not to compile. But not just that, it runs all my acceptance tests and unit tests automatically, and immediately it's back in my face. My own bug is immediately highlighted to me. I've just, if I've caused a defect, it's very in your face. It doesn't allow me to break the system. So that's continuous integration. Continuous integration is all about the code in main is always deployable. It's always in a stable as possible state. And in the continuous delivery process, there's various flavors of it. So one flavor is, for example, to automatically compile all the code and push it onto a staging environment, which is effectively simulates almost like a production environment, like maybe the code involves different pieces, so different applications need to function together. So then the staging environment simulates those different applications, maybe in Docker containers, or perhaps in like serverless, so in a serverless replication environment. And then these tests, then like the tests, integration tests, are then run on this mocked environment. So as if it's a real world sort of deployment. And then sometimes in some contexts, maybe some users have access to perform some manual checks on this environment. And then the idea is then from this environment, just pushing to production is either automatic or it's done by the click of a button. So it's like the idea is no one needs to go and compile copy files over and deploy and install an executable. Deploying to production is a click of a button or automatic. Okay, so what I'm going to explain now in the context of continuous delivery might surprise you. You might find it counterintuitive, or you might not believe me. But if you don't believe me, it's all the more reason to go and read the book called Accelerate, published in 2018. I would highly recommend this to any organizational leader, as well as people with who have technical expertise. So this book was a study done, and the study finds that there's no trade-off between speed of delivery and quality when it comes to delivering software. Now that might sound counterintuitive, but in fact, there's even data suggests that there's even a positive correlation between the speed at which teams are able to produce changes and the quality that they produce. There's a positive correlation. And then another key finding is that everything points to people and practices and ways of working first, and that's more important than the stack that you choose, the clever architecture or architectural design patterns that you choose and adhere to, and maybe the coding language that you pick. It's more people and ways of working, and the way you collaborate with your team is more important. So everything I say later about coding paradigms, just take note. It's obviously people, like the way your team works together, is more important than that. So it's just some highlights. So teams. So these are stats and case studies from the book. You can go check it out yourself. But just some highlights. So teams who would implement continuous delivery have a 90% lower defect rate. And also a key one is there's 44% more time to spend on new work as opposed to spending more time on bug fixing and dealing with legacy code or code debt. Talking a bit about continuous delivery and user expectations. If I download a new application on my Android device that was perhaps recently published, I expect changes. I expect almost daily updates. Tomorrow, if I open the app, I might see a new feature. I see a note about this has now been released, or looking for this feature, it's been removed, sort of note. That is totally normal for me to expect from sort of a fail fast mindset that is employed by technology companies. And a lot of startups do this. You don't always know what's going to work. You need to try it out before you know the model works, or the feature works, or before you know what users like or what they don't like. But how do we feel about this agile, quick to adapt, quick to address feedback, quick to try things mindset when it comes to models that might impact a listed company's financial statements? Many of you might say, no, we can't risk this. We can't do agile in actuarial modeling. So I want to challenge that mindset today and ask, but what if this approach were to put a user's life at risk? So we'll be looking at the automotive industry. So looking at a case study of a industry that is a high risk. So when any failure can lead to severe consequences. Looking at a case study where they employ continuous delivery, which includes the ability to quickly deploy changes. So Tesla is a really good example of this. They automate their production and testing and deployment process as far as possible. So some would argue that this could be given how far they are and how developed their system is and how sophisticated their system is. Other EV manufacturers will never be able to catch up. So some even argue that. But so just to walk through their process a little bit. So ECU is electronic control unit, I think, and so this is basically embedded systems coding, and this is sort of like the more software like as you and I know it. So they would push changes, and there's a continuous integration process, and then there's an automated pipeline or a process which basically just links everything together, and then they have an automated way of running all the integration tests on these control units. For example, the side range radar, everything. There's a test. There's a hypothetical virtual test bench, and then there's a physical test bench as well, where everything is automated. And then so that the blue parts are fully automated, and I think, as I understand it, the reddish pinkish parts are less. There's some manual process involved, so someone needs to go and actually either perform a manual test in order for the process to continue, or approve or sign off on something. So some of this might be legal acceptance. So there's to some extent all the legal requirements are automated, but in some case, like there is just a manual process involved in actually pushing this change. And then once this change goes through, it's literally just deployed to vehicles that are busy driving. So to this extent, it's to this extent that Tesla trusts their continuous delivery system, and this actually enables them to adapt to market demands really, really quickly. So yeah, you can go read up about this, but there's a case study where they were able to change the charge rate on one of the Tesla models from a certain kilowatt to like a different charge rate, and they were able to do this within minutes. So effectively, what the book Accelerate concludes is that it's really continuous delivery, and yeah, a continuous delivery which separates high-performing dev teams from low-performing dev teams. Some key findings or key standout things for me is that high-performing teams factor in quality of the system, quality of the actuarial model from the start. They factor in quality from the start. They don't just build and then think about testing and how we're gonna test this later. They work in small batches, so you create one change, like you add a feature and you deploy that feature as fast as possible. So small batches, and then okay, there's a rigorous, relentless pursuit to automate and to continuously improve the team. So yeah, let the machines do what the machines do best, and that's repetition, quickly executing commands, and also let the team do what they do best, where they optimize learning. And then another key sort of team operational thing, the study finds that high-performing teams make everyone responsible. Everyone in the team is responsible and aiming for sort of a big picture goal. That's a sort of a more management approach comment. And then does continuous delivery work? How do we measure whether this actually works, and so the key, just what's very interesting is the metrics that were used to distinguish low performing teams from high performing teams, and that's just the change rate, the rate at which they're able to push out changes to the system, And then I guess another interesting key one is the failure rate. So high performing teams actually have a zero, like up to zero failure rate. So they never deploy bugs to production. Yeah, you can just read the stats on the rest. So how do we employ continuous delivery and take what the how do we apply what seems to be a clear distinguishing factor between low performing and high performing teams in the software industry? How do we apply that to actuarial? Well, first of all, if you just think about from a holistic picture, are you selecting software? Are you enabling your teams to be able to do continuous delivery, or are you relying on softwares which doesn't, or maybe proprietary software or legacy? You still have legacy systems in place which prevents continuous delivery. So that's the first question. Just thinking about that, how do you manage that? And then when it comes to the actuarial model, are we relying on a culture, and typically, and I've seen this, I guess I've seen this a lot, where you mark a certain model as locked, and this is now our business as usual model, and we don't make any changes to it, logical changes, and this thing should run and rerun every month, and then maybe at year end we go into a editing phase where we edit the model and make a whole bunch of changes to it, approach changes, methodology changes, assumption changes, everything, and maybe bring in some new data sources and change our approach, and then go through a really expensive user acceptance testing phase afterwards to validate the new model's results against the old model, or to just to AVIS, to actual data and experience. So I've seen this be very inefficient, and a way of improving this could be to do continuous delivery. So making small improvements and having really like a testable model, automatically testable model, and think about, when you build this model, how am I going to test this, and how am I gonna ensure quality and reduce the need to go through very expensive manual testing of models. And our last topic is programming paradigms. So most of you who have coding experience have probably at some stage seen or heard of or used object-oriented programming, OOP. So basically it's thinking about your code and the way you structure your code in classes, and objects being instances of these classes, and you design them with certain like implementation logic. You use methods and attributes, and using methods and attributes is how you actually implement the logic of your application. And there's certain key principles here: encapsulation, inheritance, polymorphism, abstraction. Some of these things can be quite hard to understand. Some of them are actually quite simple. It just sounds fancy. But yeah, so if you don't know what this is, maybe you should go and read up about object-oriented programming. If you don't know what these terms are. Given that this is the more common paradigm, I'm going to skip on to functional programming. So the link, I've posted a really useful link in understanding the difference between functional and OOP. I'll post that in the comments of this session. Functional programming is basically thinking about your code in functions. So these functions have a given input and produce a certain output. Very simple. It originated from the academic field. I imagine a bunch of mathematicians sitting together and thinking, how can we create a programming language which reads like mathematics? So something that interesting maybe comment. So out of experience, I find that graduates from grad school, actuarial grads coming from university into working perhaps in my team who don't have a really good prior coding background pick up functional programming much easier than what they would object-oriented programming. Some people really struggle understanding functional programming. I mean, if you look at some of those terms, so currying, lazy evaluation, higher order functions, we go, what does it really mean? I would really recommend, if you're interested in this topic, go and read about this. It's really, really powerful. It's a functional programming is a whole new world if you come from an object-oriented background. And yeah, as I say, a lot of people do struggle to grasp the concepts and become proficient in functional programming. A lot of universities I see teach this in computer science in postgraduate only. So I think it's some also associated with a more difficult approach. But I'm of opinion that we should rather teach this in grad school as opposed to object-oriented thinking specifically for actuarial candidates. Yeah, so just something just to highlight. So for example, these functions can be passed as inputs to other functions, which is really, really powerful. And thinking about it in mathematical terms, if I define a function in just math notation, I can create that in my code, and I can reuse that even as a parameter to another function or a parameter to a class or something like that. Functional programming is typically best when it comes to applications where there is no state. So what that means is a certain application while it's running, it doesn't need to listen for external events while it's executing. So something like an actuarial model is like that. It's not like it'll listen for certain business events while it's busy producing results. It's stateless in the sense that there's a certain event that triggers it, and there's a certain output that comes out of it. So most data science, most actuarial modeling works like this. In functional programming, you avoid mutability. So I would argue that this helps to simplify the debugging process a lot. You're not reliant on a certain mutable variable that's sort of that keeps track of state while you're looping through certain data sets and stuff like that. So that's something that you have to try to avoid. There's an anti-pattern in functional programming. And functional programming, if done right, and if you know what you're doing, it really does improve code readability, transparency of what's happening. It's very nice to apply domain-driven design, ubiquitous language as your functions, using like the function names of verbs, and it just helps for general maintainability. That's what we've experienced as a team. So obviously object-oriented programming is here to stay, and it is like a lot of people would argue that maybe what I'm saying maybe would disagree with me, but a recent trend is, and this is like a consensus by many of the sort of the software industry leaders, is that to use functional programming for the stateless parts of your application, and then using object-oriented programming for stateful parts of your application is actually a great way to build your application, and a great way to use this. So this could be, for example, like the way you do your data modeling. So if you need to build a data model and the data needs to change, so maybe think about a claims handling system. So there's someone reports a new claim, that claim gets updated in the system. Often and the application that you're building needs to deal with that. Often object-oriented is a better approach. And then to use maybe functional programming for the data processing part of whenever you have to do where you have to perform like complex calculations or maybe some like stateless modeling. And my opinion is that functional programming is actually better for most actuarial modeling use cases. To conclude, summarizing the main points, I've obviously covered a lot of different topics, hopefully have raised a lot of questions, and I do hope you've enjoyed listening to this. I've said this a lot, but it is my opinion. This is an opinion piece. But something that I do want to share from experience is that building good software is hard. And building a good process around how to, like figuring out how a team works together to, for example, do continuous delivery is very, very hard. It's taken our team years to figure out, and we're still learning a lot. Yeah, so but obviously we face our profession faces this challenge of the software industry is becoming more interlinked and influencing our field through data science and through machine learning practices. The fields are becoming closer and closer together, or at least we as actuaries need to delve more and understand that field a lot better. So in conclusion, it's very important to understand and look closely at best practices and findings in the software industry. We need to keep our eyes focused, or like our eyes and ears open to learn and adapt, just like the software industry is also learning and adapting. Yeah, and that's the conclusion of the session. I would love to answer your questions. Please send me an email, add me on LinkedIn, send me a message, anything. I'm very happy to chat. I'm passionate about this topic, as you can probably tell. And yeah, I hope you enjoy the rest of the conference.